Hello, this is Mr. Best. Welcome to Chapter 2 of Core Connections Geometry. Homework questions 8 through 12. Find the area of each rectangle below. So on part A, we have area is equal to length times width. So on this one, we have 11 times 3. So therefore, the area is 33 units squared, or squared units. In this case, it's centimeters, so we'll do centimeters squared. On part B, we have 3x instead of 3 times 11. So kind of almost the same thing where we have 11, but now instead of times 3, it's times 3x. So what is 11 times 3? That's 33. And then the times x just follows, so that's 33x. And once again, this one is measured in units squared since it doesn't have a unit on it. And then on part C, this rectangle is broken up into 4 areas, so we'll just do the first one, this little box right here. Length times width is 3x times 11x, so that would be 33. X times x is x squared. Then we have negative 4 times 11x, so that's negative 44x. Down here we have 3x times negative 2, so that's negative 6x. And then on this one we have negative 4 times negative 2, which is a positive 8. So I'm just going to highlight real quick. This is the area of each of the individual rectangles that we're looking at. And so if we add those all up, then the area is equal to, now we don't want to combine, or I should say we want to combine only the like terms. So 33x squared, there's no other x squared, so we can't combine anything there. We can combine those two. You have negative 44x and negative 6, so that's negative 50x, and then the plus 8 is the constant. So 33x squared minus 50x plus 8, and then once again we don't know the units, so we will do units squared. Question 2-9. May puts the shapes below into a bucket and asks Brian to pick one out. What is the probability that he pulls out a quadrilateral with parallel sides? So for part A, we're looking for how many total options do we have, and there are a total of 6, and then which ones are quadrilateral but also parallel sides. So the triangle's out, that's not a quadrilateral, that's not a quadrilateral, so we have 4 remaining. Which ones also have parallel sides? So since this is a square right here, we know the sides are parallel, so that's good. Right here by the markings, it indicates that this trapezoid has those parallel sides. And then on the parallelogram, we have 2 sets of parallel sides, so that one's good. Now the kite does not have any parallel sides, so that looks like we are left with 3 out of 6. And so that would be either 1/2, or if we want to write it as a percent, 50%. On B, what is the probability that he pulls out a shape with rotation symmetry? So let me erase that, and then let's look at rotation symmetry. So what do we have here? The square, let's start with maybe the easy one to see, has rotation symmetry. From the center here, you could rotate it at around 90 degrees. So that would work. This triangle is an isosceles triangle, so rotating it would have to be equilateral, so that one won't work. The trapezoid, it's not an isosceles trapezoid and might not matter anyways, but there's no way to rotate that, so that one's out, that one's out. Not equilateral, so that won't work. The parallelogram, what happens if you rotate the parallelogram 180 degrees? You'll notice that it does have rotational symmetry, so that one looks good. And you can use tracing paper, obviously, as well as you guys are doing this one. And then the kite, there's no way you're going to be able to rotate that around. So it looks like we have a total of 2 out of 6 possible, or 1/3. And if you write that as a percent, you are going to have to write it as an approximation, unless you wrote it 33 and 1/3, but we'll just call it approximately, not exactly, but approximately 33%. Question 10. Camille loves guessing games. She's going to tell you a fact about her shape to see if you can guess what it is. A. My triangle has only one line of symmetry. What is it? So for it to only have one line of symmetry, equilateral would then be out, because that could have 3 lines of symmetry. So what would we need to have one line of symmetry? And to have one line of symmetry, we would need it to be an isosceles triangle. All right, and so think about that. If you have an isosceles triangle here and here, your line of symmetry would always break that up. B. My triangle has 3 lines of symmetry. What is it? Well, we just kind of talked about that. To have 3 lines of symmetry, your triangle would need to be equilateral, and then once that happens, you'll have all 3 of these lines to break it up. So this would be an equilateral triangle. And then the last one, C. My quadrilateral has no lines of symmetry, but it does have rotational symmetry. What is it? Well, from the previous problem, we just talked about a quadrilateral that has rotation symmetry, which is the parallelogram. Does it have, can you reflect it? And that's kind of what this question has. It has no lines of symmetry, okay, but it does have rotation symmetry. So this looks like we are looking at a parallelogram. Question 11. Jerry has an idea. Since he knows that an isosceles trapezoid has reflection symmetry, he reasons that means that it must have 2 pairs of angles with equal measure. He marks his relationship on his diagram below. So you can see the isosceles trapezoid. So let me change colors here. It means that isosceles, we have 2 equal sides, so it have to be those 2. And then you can see the angles that are marked. So this angle is congruent to this angle as he's marking. And since it has 2 arcs, then that means those 2 must be congruent. Copy the shapes below on your paper. Similarly, mark which angles must have equal measure due to reflection symmetry. So move up here. And so what angles must be equal, have equal measure due to reflection symmetry? Well, where could we reflect it? So if that's our line of reflection, and you picture, taking this point and reflecting it to the other side, then that means this angle and this angle must have the same measure. All right, so we have equal measure here. Any others that we would see? And it doesn't appear because these other angles are being split up. On B, it's an isosceles triangle, so if we split with that one line of symmetry right there, once again, visualizing the reflection from this point over to this one, then that means this angle and this angle must be of equal measure. The regular hexagon, there's lots of ways that you have a line of reflection here, so just to kind of show you a couple. We can go here, here, and here, but remember we also can go through all the midpoints, or the middle of each of the side links. So we have 6 different ones, and if that's the case, what's that going to mean? Well, let's just go back to 1 so we can kind of see it here. So if we did that, we can see that this angle and this angle would be the same, and then this one and this one would be the same. So as of right now, we might feel like those are different, but if we then go and draw on another one, let's go this way. Then now, this angle and this angle that we weren't sure about being the same, now we can see that they are also the same. So what we find out is that all of these angles eventually will represent exactly the same measure. All right, and then what about a rhombus? So a rhombus, your line of reflection, remember the side links are the same all the way across, so then this angle here would be the same as this angle. And then if you went the other way and you split it this way, then this angle and this angle would be equal as well. I'm just going to erase this one so we can see everything. So these would be our two pairs actually have equal measures for angles. Question 12. Larry saw Javon's incomplete Venn diagram below, and he wants to finish it. However, he does not know the condition that each circle represents. Find a possible label for each circle and place two more shapes into the diagram. So what could we label the first circle? Well, since it appears we have an equilateral triangle and an equilateral rectangle or square, let's go with this side being equilateral, and then see if we can figure something out for the other one. What about the right circle, since we don't have another picture on that one? Well, it has four sides, so maybe we possibly could try quadrilateral and see if we can make this work. So based on the picture, that works. We have equilateral on the left circle and quadrilateral on the right, and the intersection is a quadrilateral, which is also equilateral, and that's a square. So if we're going to do this, though, we have to place two more shapes into the diagram. So where could we place one of our shapes? Well, if it just needs to be equilateral and not a quadrilateral, then you could go to one of our other polygons. We could do a pentagon. That's not really a good equilateral pentagon, though, or a regular. Maybe I'll do a hexagon. Maybe I can do a better job of that one. Yeah, not the best. But you get the idea. So each of those sides would be the same length. And then what about another place on here? Well, what has four sides and is also equilateral? We could put a rhombus in the intersection. And then what's a quadrilateral that's not equilateral? We could do a lot of different things, but we could do a rectangle as one possibility there. So I think that answers all the questions. Is, create two conditions for each circle and then place two or more shapes into the diagram, and I went ahead and placed one in each part. You could also place one on the outside that is not equilateral or a quadrilateral. So we could do something like a scalene triangle where they're not equal. So that's a possibility as well.